the splitting in octahedral complexes. Octahedral complexes. So in the octahedral complexes, number of ligands are 6. Okay, and these point charges will interact with the orbitals or d orbitals of the metal atom. So initially, these are the 5 d orbitals. Which are degenerate. Orbitals. So whenever the ligand approaches the central metal atom, slowly what happens is the energy of these 5 orbitals will increases to the same extent. So this is the average energy. This is the average energy in presence of spherical field. Spherical field. In the case of actually the octahedral complexes, we can see here the corresponding 6 ligands will approach. You can see that the corresponding 6 positions of the octahedron. 6 positions. So that's why, here first when the field is spherical in nature, slowly there is increase in energy of this. The same time what happens is, here the corresponding energy will further increases. And wherever we have the approach of the ligands along the axis, we can see there is a more interaction of the axial orbitals. So what are axial orbitals in actually? dx square minus y square and dz square. The energy of those 2 orbitals will increase in the case of the octahedral complexes. So crystal field splitting in the case of the octahedral complex, if you see the ligands which are approaching the central atom, so automatically the interaction of the ligands with the corresponding orbitals where the lobes are present along the axis will interact more than the non-axial orbitals. That's why the energy of the corresponding dx square minus y square and dz square will be increases more to greater extent. So that is, see here, this we can represent like this. So there are 2 orbitals which are dx square minus y square, dz square, and the remaining 3 orbitals which are dxy, dyz, dzx or xz. So these have lower energy, as I already told you. These are actually Eg set. This is T2G set. This is Eg set, this is T2G set. It is having 3 orbitals. Eg is having 2 orbitals, which are dx square minus y square and dz square. This is how we can see. Now the splitting, if we come across, this splitting will be about here by 3 by 5. And here this is by 2 by 5. This we call it as d orbital splitting or crystal field splitting. This is nothing but 0.6 delta O, nothing but 0.4 delta O. Here O stands for octahedral. Okay. This splitting we generally call it as a crystal field splitting, and the energy is called as crystal field stabilization energy. Crystal field stabilization energy, that will represent like this. Of course, this delta O will be equivalent to 10 dq. That's why we can also write this as 6 dq. This also as 4 dq. That means here the orbital which is increasing energy. So here we have two orbitals. Each orbital increases its energy by 0.6 delta O, or simply 6 dq, or 3 by 5 delta O. But how many orbitals are there? Two orbitals. That means these together will increase the energy by into 2, means 6 by 5 delta O. And how many are there? 1, 2, 3. So 3 into 2. That is 6 by 5 delta O. So this much they will increase their energy. In the first case, this much they will decrease their energy. This we call it as crystal field splitting in case of the octahedral complexes. Octahedral complexes. And very important thing is here, why these two are having more energy when compared to this means the ligands which are approaching here compulsory will interact more with the axial orbitals, where the orbitals which are present along the axis, which are these two, that's why they will interact more with these orbitals. So automatically, because of the field interaction, the energy of these two will increase more. At the same time, these are least interacted. So energy of these three will be generally decreased to this extent. 2 by 5 into delta O, this by 3 by 5 into delta O. This is increase, this is decrease. The same you can represent in the form of this CFSE, crystal field stabilization energy, which is delta O, which is equal to 10 dq. Now coming to the point, whenever we come across about the filling of the electrons in this corresponding orbitals, here initially these three are having lower energy. So definitely if we come across about the filling of the electrons, we will generally follow the corresponding rule. Suppose it is these three are degenerate, so definitely we will follow the Hund's rule. Suppose we want to fill one electron, yes, this will occupy the lowest energy level. And at the same time, fill the second electron, yes, this will occupy this level. Take a third electron, yes, this will occupy this level. But coming to the fourth electron, it have two options. That means the fourth electron may pair up here, or it may enter this atomic orbital. This orbital is having more energy. That means it may enter into T2G set, or it may enter into EG set. I am discussing about the fourth electron to be filled in the corresponding these orbitals which are splitted. After splitting of the d orbitals, it is having two options. Okay, so in which case this will enter in this particular orbital, or in which case it will enter in this particular EG set of orbitals. Suppose, assume the electron is entering in this particular orbital, means this electron will get paired up. This we can understand by considering one as delta O and also P. Here P is actually called as pairing energy. Pairing energy. So whenever, suppose if I come across delta O is greater than P, or delta O is less than P, that means here pairing energy, if I come across this, is smaller. Delta O is greater than P. Delta O is greater than, that means pairing energy is smaller. In the second case, pairing energy is higher than that of the delta O. So whenever the pairing energy is smaller, in such a case, generally what happens is the pairing will take place. If pairing energy is higher, in such a case, generally the corresponding electrons do not pair up. Okay, so that's why, so we already discussed in briefly that about especially the field given by the corresponding ligands. So we'll having different kind of ligands here. the ligands like strong field ligands as well as weak field ligands. So in the case of the strong field ligands, in presence of those strong field ligands, what happens is the pairing will generally occurs. The pairing will generally occur. Suppose if you come across about Cn minus. Cn minus is a strong field ligand. So in presence of this, what happens is, so if you take for example here, so we have to fill the fourth electron. So in presence of the Cn minus, the electron is forced to enter into the T2G set of the orbitals. In such a case, what happens is, this pairing will take place. So we want to enter or fill the fourth electron in the corresponding these two set of orbitals, the pairing will take place in presence of the strong field ligand. Strong field ligand. Suppose the ligand like water molecule, this is the weak field ligand. So in presence of this, the pairing do not occur, then what happens is, the electron will enter into the EG set. EG set out. So that's why, so the pairing of the corresponding electrons or the fourth electron may enter into the corresponding T2G set or EG set of the orbitals. That depends on the corresponding ligands what are involved. For that, you have to see here, you can see here the field of ligands corresponding. So generally I minus, which is iodide, will show smaller field when compared with bromide. Br minus. This will show smaller field when compared with the sulfide, S minus 2. S minus 2. And less than SCN minus will show us less field when compared with OH minus, which will show smaller field when compared with oxalate C2O4 minus 2. This will show smaller field when compared with water molecule. This will show smaller field when compared with pyridine. This will show smaller field when compared with ammonia. This will show smaller field when compared with NO2 minus. Of course, we can have EN, ethylene diamine. This will show smaller field when compared with NO2 minus. And this will show smaller field when compared with CN minus. Show smaller field when compared with carbon monoxide, CO. So the maximum is shown by carbon monoxide, highest field. So that's why when we come across about CN minus or carbon CO as ligands, definitely you can see here the strongest field ligands. So in presence of them, the corresponding electrons will be automatically paired up. As I have seen here, so fourth electron, yes, it will paired up in presence of the strong field. So that means from left to right, if you move, the field strength of the ligands automatically increases. So almost the ligands before water, and from here to including water, they are all actually weak field ligands. The ligands after water, there are strong field ligands. Strong field ligands. That's why in presence of the strong field ligands, the corresponding electrons will pair up. That's why if you take fourth electron, yes, it will pair up in presence of the strong field. Fifth electron also will pair up. Sixth electron also paired up. Now the seventh electron will enter here. So here for the fourth electron will get paired up. Fifth also get paired up. Sixth also get paired up. Now seventh will enter here. In presence of the strong field ligands. Strong field ligand. And if in the case of the weak field ligand, so first electrons will enter like this, fourth electron will not pair up, it will enter into the EG set, and fifth electron will enter like this. then sixth will come on, pairing up takes place. This is how we can understand how exactly the corresponding electrons, whether they get paired up or not, that depends on the corresponding ligands. So this we call it as a spectrochemical series. So based on the field created by the corresponding ligands, they are all arranged like this. So whether we have to understand whether it is a strong field ligand or weak field ligand. So in presence of the strong field ligand, in the case of octahedral complexes, the fourth electron onwards, what we can observe here, first completely T2G set will be filled completely. Then only the seventh electron will enter here. In the case of the weak field ligand, what happens is, after filling these three T2G set, the fourth electron will enter into the EG set, fifth also will enter into the EG set, then sixth onwards we can see pairing will take place. This is how we can observe the crystal field shifting in the case of the octahedral complexes. Octahedral complexes. This is the last one is the spectrochemical series. Complexes. So in the case of tetrahedral complexes, let us see here, we have only 4 ligands. So in order to understand this, how the ligands are arranged in the case of the tetrahedral complexes, just assume one cube. So cube is having totally 8 corners. 8 corners. In the case of the tetrahedral complexes, here assume the ligands are present at the alternate corners, and coming to central metal is present at the exactly center of the cube. At the center of the cube we have central metal atom or the central metal ion, and at alternate corners place one ligand. That's how we can see the corresponding ligands in the tetrahedral complexes. Okay, and let us see how the corresponding d orbitals will undergo splitting in the case of the tetrahedral splitting. In the case of the this kind of orbitals, we can see here dxy, dyz and dzx. So these will present towards the center of the corresponding edge. These will face toward the center of the edge. So this is the cube. All the sides are equal. This is the cube, all the sides are equal. So these are actually edges here. These are the edges. Yes, edges, center of the edges. So dxy, dyz, dzx, nothing but we are saying the T2G set. In the case of octahedral we are saying no splitting. So those 3 orbitals, what happens is they will occupy the corresponding, they will move towards or point towards the corners, especially the center of these corresponding edges. And coming remaining 2 orbitals, dx square minus y square and dz square. dz square. See here, they will point towards the corresponding phase centers. This is a phase, no? Phase center, phase center, phase center, all these phase centers. So final conclusion here it is the T2G set. What are they actually? We have 3 orbitals which are dxy, dyz, dzx. The remaining 2 dx square minus y square and dz square. So these will point towards the phase centers. These 2 will point towards the phase centers, and these 3 will point toward the center of the each edge, corresponding edges, center of the corresponding edges. So if you compare here, I told you here the corresponding ligands are present at the alternate corners. Alternate corners. So if I compare the distance, position of this one and this one with respect to the corresponding ligands, position of the ligands in the tetrahedral complexes, which are near means these 3 are near, because these are pointing towards the center of the edges. These are pointing towards the face center. So distance from the corner to center of the edge is small when compared with the distance from corner to the face center. That means these are close. These are close. That's why these will interact more with the ligands. That's why energy of these three will increase and energy of these two will decrease in the case of the tetrahedral complexes. That's why in this particular case we can see here, first initially we have degenerate 5 orbitals. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Degenerate. Now when the ligands are approaching at the symmetrical field, they increase the energy to the same extent. So this is average energy again of the orbitals in symmetrical field. Symmetrical field. Now after the corresponding splitting, we can see the first highest energy will be for 3 orbitals, that is dxy, dyz, dzx, and low energy for dx square minus y square dz square. So this is how we can see the splitting in the case of the tetrahedral complexes. So these three will have more energy and these will have the higher energy. So this difference in energy we call it as, there we used delta O, here we have to use delta T. T stands for the tetrahedral splitting. Crystal field stabilization energy. And we'll compare the energy delta O and delta T. Here this energy is smaller when compared with delta O. The reason here we have a total of how many ligands? 6 ligands. Here we have only 4 ligands, that's all. At the same time, the gap, or because of the interaction, there is no much increase. Interaction, that's the energy if we come across in overall. So this will be 6 ligands we have. This will be only 4 ligands we have. So difference in energy by 6 by 4. Simply 3 by 2. And due to only 4 ligands, and also see here again another 3 by 2. So multiply these two, that is 9 by 4. 9 by 4. That's why here delta O is nothing but 9 by 4 into delta T. Which is higher here? This is higher. That's how we can see in the case of the tetrahedral complexes. And coming to square planar complexes, how we can see the crystal field splitting in the case of the square planar complexes. Square planar complexes. In order to understand this, let us take remove one ligand at the z-axis, along the z-axis. That means these z-axis is not having any ligands in the case of octahedral. So we have seen the case of octahedral. So first we can see here, first there are 5 degenerate orbitals. So dxy, dyz, dzx, dx square minus y square, dz square. So in presence of the symmetrical field, so these 5 also increase energy to the same extent. Average energy in presence of the symmetrical field. Now let us see how this particularly will increase the corresponding energy in the case of the octahedral field. In the case of octahedral field, I told you there will be 2 orbitals here and there will be 3 orbitals here. Up to this, okay. So this is dx square minus y square dz square. This is dxy, dyz, dzx. So up to here this is octahedral splitting. But if in order to understand this tetrahedral, square planar complexes, just remove one ligand along the z-axis. That's why among these two, this will interfere least with the ligands. That's why among these two, in the case of the square planar complexes, the interaction here it is more. That's why, so this also will split into two, where the energy of this will be less than this. This will having more energy, is having the less energy. So that's why here we can also observe among these two, again further splitting will be observed. This will be dx square minus y square. This will be dz square. And here wherever you have these two will have less interfere with the corresponding ligand. This is having more interference. That's why there occurs again splitting here, and this will be dxy. And the remaining two stabilize. This is dyz, sir. Venkatesh here. We can see here how these will be splitted. Now, in presence of the tetrahedral, if we see up to here octahedral followed by splitting here, and exactly in the case of the square planar complexes, there is further splitting where the energy of this will increase further. This is dxy. So this will be dz square. This is how we can see splitting, and further we can also see here the arrangement of the orbitals like this. So this is dyz, dzx. This is dz square, and this will be dx square minus y square. So if you see the arrangement of this particular energy here, so dyz will be equal to dzx, which is less than dz square, which is less than dxy, which is less than dx square minus y square. This is how in the case of the splitting of the corresponding orbitals in the case of the square planar complexes. So first we have to see here how it undergoes. Up to here as usual with respect to the octahedral splitting. Then this will undergo further splitting, or degeneracy is disturbed here, and finally we can see in the case of the square planar complexes, this is the arrangement of the corresponding splitted orbitals. This is like dyz is equal to dzx less than dz square, which is less than dxy, which is less than dx square minus y square. Yes, this is how we can see crystal field splitting.
If you like this video, please give a thumbs up. Please subscribe to our channel to get more videos on CBSE syllabus.